We'll talk about now the most energetic cosmic rays that we have observed. And these are commonly called ultra-high energy cosmic rays. And the definition vaguely separates the ultra-high energy cosmic rays from the other cosmic rays by saying this must be well above the Ni energy. So we talk about something of the order of 10 to the 17, 10 to the 18 electron volts. But it's not a very, very clear distinction. So basically, in principle, I would prefer to say ultra-energy cosmic rays are the ones which sort of fall at the end point of the cosmic ray spectrum as we have measured it. And just as a reminder, let's have a look at the energy spectrum once more. So let me pull that in for a moment. And I use here an energy spectrum which sort of highlights the actual rates to give you again the idea of why this is so difficult to measure. So this is the all-particle cosmic ray spectrum, now plotted in such a way that essentially you can get a better idea on how steeply it drops off, and that is done by highlighting also that you drop here over about 32 orders of magnitude in differential flux, and you go 11 orders of magnitude in the energy in this plot. So actually this plot is still squeezed. You'd have to make it even more tall in terms of its ratio. And the most important part of the spectrum that we are now looking at is this endpoint here. So you could say it's maybe 10 to the 18, 10 to the 90, 10 to the 20, these last 2 or 3 decades of the energy spectrum. And why is that so particular? I mean, it's the most challenging part of the cosmic ray spectrum. Very little energy in terms of the total energy is confined to that most energetic part. So why is it so let's say interesting to look at that? And the reason is there's multiple reasons why this is important, or why this is general interest, let's say. First of all, it's of course a challenge to accelerate these particles. So the open questions that we're trying to look at is acceleration. To give you an idea why acceleration is an issue here, we already discussed this in the context of the maximum energy achievable in shock type acceleration, but there's, independent of whether it's shock or not, there's a general argument that you can make that basically tells you how much of an energy you can reach for a given size, that is dimensional size of the acceleration region, and the magnetic field that is available. Because in the end, the size of the accelerator, the dimension, spatial dimension, has to be somewhat larger than the gyro radius, that is the radius over which a charged particle will gyrate, because otherwise the particle is pretty much free to leave. So the size of the acceleration region has to be roughly the same, or maybe even smaller than the gyro radius, and the gyro radius is given by 1 parsec for an energy of 10 to the 15 electron volts, and for a B field of microgauss. And of course it changes a little bit with the charge number. So the larger the charge number, the smaller the gyro radius. And so this condition has been used to sort of look at possible sites of particle accelerations in the universe. So what you need to do is you basically fix the energy, let's say 10 to the 20, because that's the end point of the spectrum which you need to achieve. And then you basically look at the ratio of size of the accelerator times the B field, which have to be constant. Or if you plot the size versus the B field, then the size has to be getting larger and larger for smaller B fields. Okay. So let's have a look at such a plot. This plot is often called Hillas plot. Let me just pull that in here. I got one prepared for us. And this one is now plotted in such a way that we plot the B field as a function of the dimension. And this kind of plot is often called Hillas plot. So that was invented by Michael Hillas already in the 80s. And so plotted here is the size in logarithmic units, and it starts at kilometer size because that's basically the most compact type of object that you can get, which still has a very large magnetic field. And that's the neutron stars and also gamma ray bursts. Not going to talk much about gamma ray bursts, but needless to say, these are objects which produce tremendous luminosities and gamma rays in a very short time. They need to be compact. and presumably they also have a large B field. And so neutron stars basically can go up to 10 to the 14 Gauss or 10 to the 10 Tesla. So actually they would go a little bit further up here. And now you need to compare then basically each point. Let's say, for example, you take the gamma ray burst or neutron star point, which is about a few kilometers, 10 kilometers size. And it has a B field 10 to the 13, 10 to the 14 Gauss. And then basically you can compare that with a line. That's, for example, the dashed line, which is required to get 10 to the 20 electron volt protons. So as we saw in the shock type acceleration, the energy gain relates also to the velocity of the shock. So the largest velocity you can get is velocity of sound, or the velocity of light. That would be a relativistic shock. So that would be beta shock equals 1. And the maximum energy that you can obtain for a given size dimension is actually given then also depending upon the velocity. I didn't discuss that before, but the basic requirement is that the maximum energy is proportional to L n times beta times charge. So for protons, you would draw this kind of line. You see that basically you would be able to accelerate if you have a very fast shock, which is going, let's say, faster than a few percent of the velocity of light with a neutron star. Then go into sort of a few thousand kilometer size, you end up with white dwarfs. They also sort of have a large magnetic field in some cases, but they do not even make it beyond this sort of relativistic line, which is for white dwarfs very unlikely. Then places like interplanetary space, which is like our solar system, you cannot get there for sure, because you basically talk about several microgauss field over the size of a few astronomical units. However, on a similar size scale, you have active galactic nuclei, which are known to harbor a massive or supermassive black hole with maybe millions and even a billion solar masses. And in the environment of these very massive black holes, you have accretion happening and you have jet launch happening. And we know from various observations that the B field that you can get there can reach up to several Tesla. So that would put us roughly up here. So there would be a good chance that you could accelerate ultra-energy cosmic rays. Then going a step larger, you basically end up with supernova remnants, which we discussed before, which are sort of at the size of maybe parsecs when they expand a lot. And however, the B field is not going to be much larger than several microgauss, which means that they fall short a lot, but they still would be able to accelerate cosmic rays to the energies that are required to explain galactic cosmic rays. If you go now for the entire disk, disk has microgauss, that's the galactic disk, 10 microgauss or so, few microgauss. And it's got the size of the disk thickness, which is of the order of maybe 800 parsecs or maybe up to kiloparsec. And then if you go beyond that, the halo would be sort of several tens of kiloparsecs. The B field would be about the similar and still falls short. But it pushes energy quite high. You probably get cosmic rays accelerated up to 10 to the 17 or so if you have a fast shock forming there, which we don't have evidence for actually. Then these active galactic nuclei, which start out at the size of a few astronomical units, they launch jets which extend up to several kiloparsecs into the ambient medium, and they drive standing shocks, which are known as radio galaxy jets and radio lobes, which are sort of at the size scale of several kiloparsecs. And they would also be falling in a region where you could, under favorable conditions, actually start accelerating particles up to 10 to the 20. Galaxy clusters, they have sizes up to megaparsec and maybe even B fields of microgauss in that medium. So they would also fall in that region here. And finally, intergalactic medium as such, it's kind of interesting to note, could have fields up to maybe 10 nanogauss or nanogauss, and they could be sizes of gigaparsecs. So in principle also acceleration could take place, even though the B field could be also much, much lower than that. So that thing basically we don't know, that could go much lower here. So there's only few astrophysical objects which do fulfill this basic requirement to be able to accelerate cosmic rays to very high energy, to ultra energy energies, even to 10 to the 20. There's also a sort of thing which should be mentioned here. This is just the maximum energy you can obtain, assuming that there's no other losses. So losses are ignored in this case. And we know in the acceleration losses are of course crucial. And the other thing which is to point out is that if you are basically talking about objects which are sort of having gyro radii of several, let's say, megaparsecs over here, you can see that the distance under which we see these sources is not much larger than the size of the gyro radius. And if you compare that with the gyro radius of our halo and our disk, you notice then that these objects, they would be traceable because, at least for a proton, the gyro radius is so large that basically the sources start to be visible and the cosmic ray arrival direction would point back to the sources. So we can do real astrophysics with ultra-energy cosmic rays if they are from these kind of sources, because you can trace them back. So I should also note that people have been coming up also, since this is an obvious problem, right? So you need to understand how you can accelerate particles in order to explain the observations. That's the minimum criterion you have to meet. And that even falls short in most cases, that you do not really see a comfortable, let's say, size and magnetic field combination which would allow to get this very energetic cosmic rays out. And this is even ignoring all these things that, for example, the shock will be having a finite lifetime as well. There will be all kinds of issues which are not included here necessarily. That basically goes down to the point of acceleration is really an issue. And there has been some discussion that maybe some of these cosmic rays are actually not accelerated, but they are produced by decaying relic particles, assuming that there is something which is heavier than 10 to the 20 electron volts and has a sufficiently long lifetime. It could basically decay and produce cosmic rays today. That's not favored anymore for various reasons. We come back to that a little later. So let's talk a little bit about another issue which comes up immediately when you talk about ultra-energy cosmic rays. And that is, the one thing is you need to accelerate them. So this is the first point I point out here. The second point is that they basically move, let's say a 10 to the 20 electron volt proton. It has a Lorentz factor of 10 to the 11. So that means that if it moves through the CMB, it will see the CMB with a Lorentz boost of 10 to the 11. So essentially it's like a hard gamma radiation coming towards this proton in this rest frame. So there will be photopion production. And that means that the distance over which cosmic rays can reach us is limited, and that's the so-called Greisen-Zatsepin-Kuzmin cutoff, which are expected. So let's just talk about that for a moment. So the photopion production works in the following way. It's called photopion production because the interaction takes place not with another nucleus, but it takes place with a photon. So the most likely thing that happens is you have the cosmic ray proton, which interacts with the CMB photon, and then it goes into a delta plus resonance. And that will basically then decay. Okay? And if you look at the cross-section for that process, let me just pull in a plot for that. So this is the cross-section. So you see the delta resonance has a threshold energy, which is required to excite this delta resonance. It's at the level of a few hundred MeV. And this basically means that you need to have a sufficiently large Lorentz factor. And the threshold that you need to calculate is given by a very simple kinematics. I'm not going to go through it here, but it's basically 2 times the mass of the nucleus that we're dealing with times the mass of the pion plus mass of pion squared divided by 4 epsilon CMB. So this assumes head-on collision between a nucleon of mass mn, and this basically takes the threshold energy so that you can start producing this. The actual peak in this threshold, peak in the delta resonance will be achieved a little bit above that value. And so this corresponds to an energy in our laboratory system of 4 times 10 to the 19 electron volts of the protons. Okay. So here, this is now plotting the energy of the photon, right? So that's the lab energy of the photon. So basically this corresponds to several hundred MeV that you need to get. And if you then know the cross-section, so this is the sigma pi gamma cross-section, then you can calculate the mean free path length. So the mean free path length would be then, roughly speaking, 1 over the number of photons of the CMB per volume element times this cross-section sigma pi gamma. And that boils down to a value of the order of megaparsecs. So that's a very simple quantity you can calculate. You can read off the value here. It's like several hundred microbarn. And then in CMB, that's the number of photons per volume element. That's about 411 photons per cubic centimeter. And this scales with the temperature. So this is assuming of 2.73 Kelvin temperature, and it scales with a third power because it's a number density. and it scales, of course, with the redshift to the third power as well. Okay, so this basically tells us that all the sources that we see, all the cosmic rays we see, must be coming from sources which are only very nearby. So it's like the local neighborhood of our solar system. So let me just also pull in a plot which gives a little bit more detail, because this is just sort of the above threshold value, but it is of course energy dependent. So let me just pull in a plot for this mean free path length. So that's the mean free path length, and so this is basically the line that we were calculating here. So this is our lambda mean free path, and then this one basically is telling you something about the energy loss. So this is lambda mean free path times the inelasticity. So let's call this the inelasticity. So that's the fraction of energy which is lost. So you see that about 20% or so of the energy is lost in each collision, which again factors this ratio which I roughly said, pion mass over the proton mass. And you see that basically at energies, the threshold would be somewhere here. That would be threshold. And you see that there the cross-section, the mean free path length drops over basically 1 order of magnitude in energy by about 4 orders of magnitude in distance. So here we will talk about, this is in megaparsecs, so at threshold we actually talk about sort of gigaparsecs. And if we go well beyond that, we basically talk about several megaparsecs. That's the value which I just estimated up there. So the standard paradigm then, therefore, in this scheme, in this schematics, in this scenario, is that we assume that ultra-energy cosmic rays are accelerated by extragalactic objects, by AGN, for example, jets, or even clusters. And the sources will be distributed more or less homogeneous in our neighborhood, neighboring universe. And then basically we would expect sort of a exponential cutoff at this threshold energy, because then basically our volume in which cosmic rays are being accelerated and can still reach us shrinks very dramatically. And we expect to some extent anisotropies, because the cosmic rays are still charged and they're being deflected in our halo field. Because there we basically deal with still some deflection that will change the apparent direction in the sky. And we also expect this to be mainly protons, because the iron nuclei actually are even stronger subject to breaking up, since that the photodisintegration cross-section is quite large. So whatever will come out is going to be moving down in mass to smaller masses eventually. So if the sources are really distributed quite far away, we would expect that we would see mainly protons left over. So let's look at some of the results of these observations. So the first thing I want to show you is this result on the anisotropy. So let me pull in 2 plots on that. So we have here 2 old sky images. So this is on the anisotropy. So let me just write that here. Do we see any anisotropy in the sky? So the entire sky is covered not by one instrument, because they are ground-based, but by 2 instruments. So the northern hemisphere, and this is Equatorial Coordinates. So that means what you're looking at is essentially the Earth coordinate system projected in the sky. So the equator corresponds to objects which are, observable under zenith angle 0 when you are looking at the sky at that particular time. And the right ascension is then basically telling you what time this object will be culminating at zenith angle 0. And so you see that the Northern Hemisphere Observatory is observing all these black dots, and that's the so-called telescope array. And the Southern Hemisphere Observatory is the Piaget Observatory. And so they basically cover the 2 hemispheres, and they have some overlap around the equator, because they are not sitting at the North Poles, but telescope array is sitting in the United States and Piaget is sitting in Argentina, so they're basically looking from mid-latitudes upwards. And from the individual points that you see here, so this is above an energy of this threshold energy of 4 times 10 to the 19 electron volts. So this is E larger than E threshold. You should start seeing actually the sources because the gyre radius gets so big. But you don't see anything particular. In the left plot, it's almost impossible to pick out any anisotropy. There may be some clustering available, and in order to check that, on the right plot, now it's plotted the arrival directions where you basically smooth over patches in the sky with 15 degrees, and then you shift sort of a smoothing kernel across the whole sky. And then the deviations are shown now in standard deviations. That is, 0 would mean that it's consistent with no deviation. Anything which goes at higher values means that there's an excess. Anything which goes at smaller values, you see a sort of deficit. And you see that basically the two maps combine nicely in a way that you do not see any strong change of this kind of pattern. When you go from the north to the south, you see maybe some excess here, but it's still at the level of less than 3 standard deviations. And you also see deficits over here. So basically, it means that it's all within the expected fluctuations, even though there's a lot of speculations about this excess in the southern hemisphere, because that sort of lines up in a region where you may expect something from Centaurus A. Centaurus A is actually a little bit further over here, but it's expected that there would be some deflection which would channel this emission to this patch over here. But it's sort of the conclusion, the main conclusion you would take away from this is there's no significant excess or deficit, as a matter of fact, visible, apparent. So that basically throws overboard this expectation that there's an anisotropy. Now let's have a look at the actual measured energy spectra, and that's now getting very interesting also because these results are rather recent. And so the Piaget groups, they've been, so I write that as Piaget, they've been reporting in a recent paper, and I just write down here the preprint number. You'll find that under 2008, so it came out in August last year, 06488, and there's also a second part. I just want to talk about the first part here. They report on 14 years of data that they've been taken for an accumulated exposure of 60,400 kilometers squared second steradian. Okay, so if you look at these numbers, it tells you essentially what would be the flux that you can expect to see one event of. So that would be then just the inverse of that one. And so the result of this, let me just pull in again the main result plots of this. My mouse is somehow acting up a little bit. Okay. So that's two ways of looking at, oh well, actually it's three ways of looking at the energy spectrum. Let's look at the first plot up here. So basically energy is, see it down here, it's 10 to the 19 and 10 to the 20 electron volts. So the expected cutoff should take place at around 4 times 10 to the 19. Okay. Now let's look at the upper plot first. So this is basically now the flux multiplied with E squared already in per kilometer squared per year per steradian electron volt. And so you see that most of, the spectrum drops quicker than e to the minus 2. That's why you see most of the events in this first bin. That's the number of events actually that are observed. So it's 83,143. And you see how quickly that number drops. So at threshold energy of 4 times 10 to the 19, you only have roughly 1,000 events in such an energy bin left. And then you see how the spectrum basically trails away. So you see only 6 events in this last bin here. And then there's only limits because there's no more events seen in that particular energy bins. Now, plotting that with E cubed now, so making it a little bit more apparent what the changes are, you basically see that the spectrum is quite complicated. So instead of just having sort of the anchor feature maybe here, and then basically a spectrum hardens again, you basically have another break here, and then you have a break here, and essentially there's no exponential cutoff. So what's observed is, cosmic rays are observed up to 10 to the 20. So we can say it's larger than 10 to the 20. So that's the minimum that we need to obtain in terms of maximum energy. The spectrum is a sequence of power laws. And that is interesting because we were expecting essentially that there should be an exponential cutoff. So you would expect something which sort of turns down somewhere like this. Exponential cutoff means it's really curving down quickly. Instead, you see that there's just essentially a continuation of just a break in the power law. So there's no cutoff visible. And that's kind of strange, because we said in this kind of standard paradigm you would expect that there should be a cutoff. So let's talk about what that means in terms of the interpretation of the origin of where these cosmic rays are produced. So I want to just make sure that you don't get the idea that decaying massive particles are out. They are out. And the reason for that is not so obvious from this part here, but there's no photons. The reason being is that the decaying massive particles, they would inject energy at even much larger energy than 10 to the 20, and then you would see essentially secondary particles in the form of photons coming through, and this is not the case. So let's just get that off our desk immediately. Now the second thing that we can basically say is that the model where you assume that there's one uniform source population which basically emits in a homogeneous way protons is also out. And why is that out? Well, which produces protons? Well, because we don't have a cutoff. Because in that case you would expect a cutoff due to the UHECR effect. And finally, there's also the third possibility out. That is, you have a single proton accelerator in the neighborhood, because that would lead to anisotropies, which we do not see. Okay, so the paradigm basically that was usually discussed for many decades is basically completely ruled out. And there's actually one more piece of evidence that we need to revise these scenarios that we've been looking at so far, and that is essentially now that with the PRG observations we can also determine the composition, that is, what kind of particles are actually being observed that produce these air showers. And so if you do that game and you look at the composition at the same time, and then you try to fit both the spectrum as well as the composition, you can get away with such a mixed type of model where you have now various species. So essentially this is now everything which is sort of up to iron, and then you've got the slightly lighter group here, and you've got oxygen group, for example, here in the green, and then you've got sort of like helium mainly over here, and then you have some protons over here. So actually the dominating type of air showers that observed at energies close to 10 to the 18 are protons, whereas if you go to the upper end of the spectrum, you basically realize this must be much heavier particles. And then you just basically can assume that there's sort of like a rigidity-dependent maximum energy that the sources can accelerate to, which makes sense. Then basically you do not get an exponential cutoff, but because of the overlaying of various things, you essentially produce another knee, similar to what we had at the knee energies that we discussed with respect to cosmic rays in our galaxy. Also for the extragalactic sources, we basically have sort of a new type of knee, which is basically forcing us for another scenario. So the favored scenario, let's put it, that basically comes out of this is that there's probably a bunch of AGN and maybe starburst galaxies contributing to this, which accelerate a mixture of nuclei, and they have a rigidity-dependent maximum. And then you naturally get both the shape of the spectrum as well as the composition, which changes from light to heavy. And we can basically say that the end of the spectrum is not due to UHECR, and it turns out that basically UHECR would be more or less ruled out by this, but it's more like not the UHECR, but it is really just the maximum energy which we are seeing. So in other words, the accelerators run out of steam. Then we can basically also make some statement about the power that is required to produce the cosmic rays, and then basically this ends up by taking the energy density that we see divided by the loss time. So then we would basically say that the power, the luminosity in ultra-high cosmic ray accelerators per volume element, because we do not know the volume over which they accelerate, is of the order of 5 times 10 to the 44 ergs per megaparsec cube per year. And this is simply by taking the energy density divided by the loss time. That's essentially the energy density divided by the loss time, and the loss time here is now of the order of 3 gigayears or so. That comes from the Photopine production. So that's an interesting situation, because only with this very detailed measurement of the spectrum in the cutoff region, it's been now possible to observe that, first of all, the spectrum does not curve. It doesn't look like an exponential cutoff, but it looks more like just a power law. And moreover, due to the possibility to detect the type of this particle which creates the ash showers, we can see that this is a mixed composition which turns out to be more heavy dominated at the end of the spectrum. And this basically forces us to drop the original paradigm and just move ahead with something which is completely different. That is, GZK cutoff doesn't play a role. And we are probably seeing actually sources in a much larger volume which contribute, and they basically inject even heavier species. Let me just close this section with a couple of comments on what may be just happening now and what is starting to happen and will be a dominant part of this astroparticle physics field. That is, you can imagine that what we're looking at now is essentially already using various channels to understand cosmic ray origin at various energy scales. And this is what I also introduced several lectures ago as something which is called multi-messenger investigations. And ultra-high cosmic rays are quite, I think, an important part of this, because they really favor, or we need to really work across different messenger particles and combine observations to understand the origin. So to give you an example of this, let me just again show you a plot of ultra-high cosmic ray spectrum, but now combining various messenger particles in one plot. So this is actually something which has been now pursued more and more in the past years. So here again you see now the energy of the particles that we're looking at, and here we see some flux and multiplied with E squared. Now what we see here, this measured spectrum, that's essentially what we're looking at, is the cosmic ray energy spectrum as it was measured with telescope array and Auger. Now you see that this basically requires that some of the stuff maybe still gets absorbed, right, through GZK effects, maybe less than what was thought before. But whatever is being absorbed is not gone forever, but it will produce necessarily a secondary emission. And the secondary emission constitutes, again, different particles. So in, for example, Photopine production, you will produce pions which are charged as well, and they will produce neutrinos. So you can look for neutrinos that come from this process. The photons which you inject and the electrons you inject in the intergalactic medium, they will drive cascades via pair production and Bremsstrahlung respectively. And since the mean free path length is very short for the photons, essentially the radiation will come out at an energy where the universe becomes transparent. That's essentially below about 100 GeV. And so in some sense, these measurements combined with the actual direct measurements give us an idea about how much cosmic ray accelerator is actually present. So if we think, for example, in our case, that there's a cosmic ray energy density of, or let's say the luminosity of cosmic ray accelerators is of the order of 5 times 10 to the 44 ergs per megaparsec cube per year, then this requires that some of that energy goes into secondary neutrinos and electron positrons as well as gamma rays. And here you see now the predictions from this. So depending a little bit on how what kind of mass species are present here, you do expect some secondary neutrino flux, which you can compare then, for example, with the neutrino flux measurement that is diffused in the sky from the neutrino telescopes, and you see that they are not so far off. So actually they sort of tend to explain the neutrino flux, even though they fall short a little bit here. And this line may actually go down a little bit more because of these observations which I was just describing to you. And in the second step, you can also look at what will be the gamma ray production that you can see then and compare with the old sky gamma ray emission. So basically think about this gamma ray old sky image, the stuff which comes out, which we observe well beyond the galactic plane. It's partially from sources, but partially is diffuse background. And that diffuse background turns out to be maybe some fraction of what we can see. So it's basically this kind of lines that you can draw here, which would come from this kind of cascading process, and that should not overproduce, for example. So we can basically combine gamma rays, neutrinos, and ultra-energy cosmic rays to get one consistent picture of the source population and how they're distributed in the universe.